Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today we're diving deep into DeepEP, a communication library designed to supercharge mixture of experts, MoE, models. It's all about achieving blazing fast communication for parallel expert processing.
Wow, sounds exciting. So what's the core innovation here? Is it just faster communication, or is there something more sophisticated going on?
Exactly. It's not just about speed. It's about efficient speed. DeepEP focuses on optimizing all-to-all GPU communication, crucial for MoE's dispatch and combine operations. Think of it as a high-speed highway system, specifically built for the data traffic of massive parallel models.
I see. So how does it achieve this efficiency? Is it using some novel hardware acceleration or a clever algorithm?
Both, actually. It leverages low-precision operations like FP8 for faster calculations, and utilizes optimized kernels for different communication scenarios. For instance, it handles asymmetric bandwidth forwarding between NVLink and RDMA domains, a common challenge in large-scale clusters.
Asymmetric bandwidth forwarding? Could you elaborate on that? I'm not entirely familiar with the nuances of internode communication.
Sure. Imagine you have a super-fast local connection, NVLink, and a slightly slower wide-area connection, RDMA. DeepEP's smart kernels prioritize the fast path whenever possible, but efficiently handle situations where data needs to travel across the slower RDMA network. This is particularly important for scaling MoE models across multiple nodes.
That's clever. And what about latency? In many applications, low latency is just as important as high throughput.
Absolutely. For latency-sensitive tasks like inference decoding, DeepEP offers a set of low-latency kernels that rely solely on RDMA, minimizing delays. They're designed to keep things snappy, even with a large number of experts.
Impressive. The documentation mentions a hook-based communication computation overlapping method. How does that work, and what are the benefits?
That's a really cool feature. It allows for overlapping communication and computation without using any SM resources. Essentially, while the model is performing computations, DeepEP quietly handles data transfers in the background, maximizing resource utilization and speeding up the overall process. It's like having a dedicated team handling logistics while the main team focuses on the core task.
That's a significant advantage, especially for resource-constrained environments. The performance numbers look quite impressive, especially the bandwidth achieved with the normal kernels. But, I noticed a caveat about using a non-standard PTX instruction. Should we be concerned about that?
You're right to point that out. They're using a less conventional PTX instruction for performance gains, but it's not officially documented. The authors claim it's safe on Hopper architectures, but it might not be portable to other GPU platforms. It's a trade-off between performance and portability. If you're targeting a specific hardware, it might be worth the risk, but for broader compatibility, it's best to disable that instruction.
Good point. So what are the key takeaways? What makes DeepEP stand out from other communication libraries?
DeepEP's strength lies in its specialization for MoE models. It offers optimized kernels for various scenarios, including high-throughput training, low-latency inference, and sophisticated features like communication computation overlap. The support for low-precision arithmetic and the detailed attention to network configurations, including adaptive routing and traffic isolation, make it a powerful tool for anyone working with large-scale MoE models.
It certainly sounds like a game changer for scaling MoE models. Thanks for breaking it down for us.
My pleasure. And that's all the time we have for today's Tech Bytes and News. Thanks for listening, and we'll see you next time. Goodbye.
Bye-bye.